Good morning everyone, I'm TJ and today I'm going to show you how robot companies like COMAU and IGUS can improve the path calibration and robot accuracy by digital twin simulations. And I'm going to use a system called FEDEM, which can calculate the deviation from the reference trajectory due to gear and structural flexibility and loads, and hence improve the robot accuracy with more than 90%. This slide is showing the process step by step. First, you do the programming of the TCP path in RoboDK. And then you use the inherent inverse kinematics in RoboDK to calculate the joint path. And then you use this joint path as input to the FEDEM simulation. And it calculates then the true TCP path and hence also the deviations. And then you use these deviations to update the TCP path in RoboDK. And you perform the inverse kinematics once more. And then you will have a calibrated joint path that takes into account the structural flexibility and the loads acting on the robot. And then you can use this joint path to run the real physical COMAU robot, or you can use it in FEDEM to benchmark and validate the improved accuracy, which in my experience has been more than 90% in my industrial applications. As an extra bonus with FEDEM, you can calculate the stresses and fatigue by using virtual strain gauges, and the calculations are faster than real time. And this can be used in predictive maintenance of the robot. This slide is showing the process in more technical terms. And you can program the TCP path in a COMAU device or by using RoboDK. And the systems will, based on inverse kinematics, provide the joint trajectories. And then you can use the joint trajectory in FEDEM to simulate the true TCP trajectory, which is not the same as the TCP kinematic trajectory. There will be some deviations due to the loads and the flexibility acting on the robot. And then you can use these displacements, run them through the inverse kinematics to calculate some joint perturbations that you have to add to the joint path in order to get an updated and calibrated path, taking the flexibility and loads into account. And this updated path can be executed in FEDEM to validate the improved accuracy, or you can apply them then directly to the physical robot. To demonstrate the improved accuracy by using a digital twin model in FEDEM, I've selected this IGUS Rebel 6-DOF robot. And as you can see, each structural part is meshed with a very fine, dense, solid mesh. And these are coupled together with joints and gears with correct stiffness. And this model has been validated by physical tests. In addition, I added some virtual strain gauges to demonstrate the ability to calculate strain and stress time histories in real time. The mass, stiffness and damping properties of the IGUS model was validated through static and dynamic tests, as shown on this slide. And the accuracy I obtained was 0.1 millimeter. Here you can see the validated FEDEM model in action. And I created a rectangular test pattern, and I added a payload of 1.5 kilos at the TCP. And here you can see that the average vertical deflection was in the range of -2 to -4 millimeter. This slide shows the accuracy before and after calibration. And I did run a rectangular test pattern that was programmed in IGUS IRC. And this is the kinematic perfect pattern that you want the robot to follow. Unfortunately, due to gravity and flexibility in the robot, you can see that the TCP path simulated in FEDEM is not co-located with the perfect path. There is a deviation. And in this example, I used the deviation in these 4 reference target points to update the joint path in IGUS IRC. And after I updated the TCP path and hence also the joint path in IGUS IRC, I run the simulation once more in FEDEM and I obtained this red curve here. And you can see I hit the 4 reference points spot on. I improved the accuracy with 97 to 100% based on one FEDEM simulation. And you can use this FEDEM as a plugin in RoboDK or COMAU's programming system to improve the accuracy in the same way. It's very easy to integrate this type of digital twin-based joint calibration in a robot offline programming system like RoboDK or COMAU's system. You simply export an FMU from FEDEM, and as you probably know, an FMU is a kind of zip file embedding the model, that means the FEDEM Digital Twin model, the solver, that means the FEDEM solver, and you also include predefined inputs and outputs. And as you can see here, the inputs are typically the interpolated joint angles from RoboDK or any offline programming system. And these can typically be stored on CSV files or streamed directly to the software. The outputs could be, for example, stress time histories from the virtual strain gauges or the TCP positions or the TCP deflections. So by exporting this FMU, you can include it as a plugin into any offline programming system. And then you can use this plugin to correlate the reference trajectories. Finally, I would like to add some information about the history of FEDEM. FEDEM was developed by NTNU and SINTEF already back in the 80s. And then in the 90s and later, it was further developed and used by FEDEM Technology until FEDEM Technology was acquired by SAP in 2015. And then they wanted to turn FEDEM around and not being used as an engineering tool, but a digital twin real-time simulation tool. Until then, companies like ABB had used FEDEM in order to optimize the dynamic performance of their robots. But not only ABB, Neos Robotics, Syntax Factory Automation, Sandvik Coromant, Cincinnati Milacron, and the European Space Agency. And during that period, ESA also selected FEDEM to be the reference for satellite deployment simulations, including mechanisms and robots. So, FEDEM is a truly benchmarked and reliable piece of software you can trust in your robot applications. For more FEDEM info, I would recommend you to take a look at my webpage, track.no, or you can visit my YouTube channel, where I have FEDEM playlists. Some playlists with applications and training videos, and some with digital twin applications. And bear in mind that FEDEM is now open source. SAP acquired FEDEM technology back in 2015, but they pulled out of the digital twin business in 2024, so FEDEM is now available on GitHub, and you can download the executables from openfedem.org. So I strongly recommend you to test FEDEM for robot applications, and please contact me if you have any questions. I will continuously post new robot videos and robot digital twin implementation videos from now. See you later. Bye bye.